Okay, so let's actually practice using our K's rule. So last time we learned that's how we can calculate our compressibility factor, and we treat our mixture as a pseudo-pure substance to do that. So what we have? Well, we have a rigid tank. It contains 2 kilomoles of nitrogen and 6 kilomoles of carbon dioxide. It's at 300 Kelvin and 15 megapascals. And we want to figure out the volume of this tank. We can do that in 2 ways. One, we just say the ideal gas equation of state, and 2, through K's rule. So first off, let's just do the ideal gas equation. And so with this, we know that the volume of my mixture is equal to the number of moles, my universal gas constant, the temperature of the mixture over the pressure of the mixture. Both of these are known. And the number of moles is also known. There's 8 moles of gas in there. So this is actually really easy to calculate. I plug it in, 8 kilomoles, 8.314 is the value for my universal gas constant. And all those numbers, all the correct units. When I use kilopascal instead of pascals, because I use kilopascal right here, and this is in kilomoles to match here. So just make sure everything matches your universal gas constant. Now I get a value of 1.33 meters cubed. Is that accurate? Probably not, because this is a mixture. And so we're going to need to calculate the compressibility factor. And so we're using K's rule. It's the same, right? No, we're going to get a very different answer. So let's go ahead and calculate it. Okay, so for K's rule, I have to find that the critical properties of my pseudo-pure substance. To do that, I've got to figure out the mole fraction so I can then do that kind of weighted average. So first, let's calculate the mole fraction, which is really easy. We've got 2 components. So for nitrogen, it's 2 of the 8 kilomoles, so it's a mole fraction of 0.25. For carbon dioxide, it's 6 of the 8 moles, so it's a mole fraction of 0.75. So 1/4 and 3/4. Nothing too hard here. Now we got to go ahead and get the critical properties from table A1. I want to go ahead and show this to you just so you can see where it comes from. We've seen it, I think, once in the past, but it never hurts to show these tables. So let me go ahead and jump over there now. Okay, so here we are at our appendix once again. And so if you look at the very first table, it's molar mass, gas constant, and critical point properties. Those are the ones that we want. So if I go there, it jumps to the right place. Nice. Maybe it's probably jumping pixels. I really don't know what's going on with it. Sometimes it does a horrible job. So here's carbon dioxide. I go across, I can find its critical temperature and its critical pressure. And if I want to, I can go down to nitrogen and find its critical, make sure I'm being careful here, temperature and pressure. And so these are the values I'm going to be using to plug into my equations in just a minute. So with that being said, let's jump back. Okay, here we are. So we got the critical properties for nitrogen, like I showed you, as well as for carbon dioxide. We have their mole fraction, which means that I can go ahead and find the critical properties of my mixture, which is just a weighted average. I take the mole fraction for each of those, I multiply it by their particular critical properties, and then I add all those values together. So this right here, if I'd write it out, would have been 0.25, so I was going to do a fourth, times, doing temperature, 126.2, plus 3/4 times 304.2. And that's what gave me 259.7. And then I would do the same thing for my pressure to get my critical pressure of my mixture. Now, once I have these critical properties, I can go ahead and get that reduced pressure and reduced temperature, so I can then go to that chart and find my compressibility factor. So this is not hard to do. You simply take the temperature of your mixture and you divide it by your critical properties of that mixture. And the the pressure of your mixture, and divide that by the critical pressure of your mixture. And you'll get 2 values. So I have 1.16 and 2.35. Using those 2 values, we can now go to the Nelson Obert charts and get your compressibility, which comes out to be about 0.49. So let's jump there right now and see how I got 0.49. Okay, so here we are. So I had a reduced pressure of 2.35, which is somewhere around here, and a reduced temperature of about 1.16. So I'm going to go up, I'm going to just barely pass this, and I'm going to go over, and I get somewhere around like 0.47, 0.46 for my compressibility. So went up, I went over, and I got my value. How close is that? Well, let's see. Pretty close, considering I was just eyeballing it. Okay, so I have 0.49. That's my compressibility of my mixture. So now what am I going to do? Well, I want to calculate the volume of my mixture that this tank would take up. Okay, so the volume of my mixture is simply, the whole PV equals nRT thing. We now know what the compressibility factor is. We did all that work for it. We don't use the reduced pressure or temperature when we're trying to calculate the volume at the end. Those are only used to find our compressibility. After that, just ignore them. You have your compressibility factor, you're happy. So if I rearrange this, you can see that all of this stuff is the same stuff that I saw in my ideal gas equation. In fact, that's actually equal to my ideal gas volume. So what we can see here is my compressibility factor is just acting as a correction term. I have the ideal gas case, I'm then correcting it to reality. And so in reality, I would take about half the space I thought I would take using the ideal gas equation. It'd be only 0.652 meters cubed. Now, practically, what does that mean? Well, it means this. If you were to take a tank and it was 1.33 meters cubed, and you were to fill it with 2 kilomoles of nitrogen and 6 kilomoles of carbon dioxide, thinking that you would get a pressure of 50 megapascals, you would find out, surprisingly enough, that you would not. You would have a lower pressure because you weren't filling it with as much, you had just too much space for that amount of gas. And so this is one way you could test this. You would just add in that certain amount. It's really not easy to, count moles. I mean, you're going to have a flow rate. You have a mass flow rate going through some valve. Pressures make it a lot easier for this one. By the way, this would get you very, very close. Because after all, this is not a perfect method. We're still within about 10%. There's still that 10% error possibility. But it's close. So with that being said, hopefully this helps you see how to use K's rule to calculate your compressibility factor, and then from that figure out your real gas properties from our equation of state. Thanks for watching. I'll see you all next time. Bye-bye.